Today we're going to take a brief look at the block merge sort method. Now, a lot of this sort method relies heavily on the interpretation of Wikipedia's block merge sort. And I've also tried to follow Bonsai the Penguin's write-up on block sorts as close as I possibly could. When starting the sort, I thought it was going to be a much shorter method than I was working with. However, what caused the largest and greatest jump in the amount of code that needed to be written was the in-place block sort portion for arrays larger than 32 items. What I'm going to do is I'm just going to briefly walk through each of the methods for this sorting algorithm. Again, it's not going to be a super in-depth walkthrough because there is just so much code here. And I'm going to then show that the code that I have works for the spec provided for the challenge. However, it still needs some tweaks and some adjustments for large arrays of numbers. But we're going to stick to the RSpec and deal with those bugs at potentially a later date. But again, there are bugs for arrays that are larger than, right now, 16 items. I'm still working on the in-place merge for larger arrays than that. So let's go ahead and walk our way through it. Now, this is supposed to be a big O1 memory usage algorithm. Everything is sorted in place. However, there are buffers and caches that are built into the algorithm that still allow that O1 because they're not dynamically being built on the spot. There are portions of memory that are already set aside for this sort, or they are buffers built into the original array itself. So the first thing I do is I set up a global cache variable that will basically create a cached method or a memory unit of 512. Now, again, this is just a cache to be used for that in-place merge. It won't, depending on the size of the array that's passed in, it will not completely be filled. However, if larger arrays than 512 are to be sorted eventually, what it will do is create a sort of buffer that can be swapped in and out of as we're dealing with that in-place merge. The next method I built is just a simple swap method. I built this simply because even though we can do a parallel swap in Ruby, it doesn't always fit on one line, and so just a simple swap method should permit me to parallel swap the items on one line without building larger methods than are necessary. And it's a simple swap method that swaps one value with the other. The next was an interesting method, and this is a method that borrowed heavily from Bonsai the Penguin, who I believe borrowed it from Hacker Daily. So what this does is it takes a number that's passed in and it will floor it to the nearest binary power, or power of 2. So if 5 is passed in, 5 is less than 8 but greater than 4, so it will return that number 4. Again, it's that binary root that's going to be returned for that. Now, the reason that we're using this method is to create array or subarrays within the original array that are as close as possible to being of equal size, because when merges happen of equal size, it is about 10% more efficient to merge those than if you have two arrays that are different sizes. The next is just a simple linear search. So we are searching through the array for a value and returning the index at that specified value. Okay, then we have a binary search, but we have two separate binary searches. The first binary search will find the first place to insert a value in order, and that's before a value. And then the binary last will insert or find the index to insert a value after another value. Then we have these methods that use these binary searches to actually do the inserting. So again, it's the find first forward method, find last forward method, find first backward method, find last backward method. Again, these methods are being used, or the binary searches, or using the binary searches to place items within the array in place. So it's going to be setting sort of a buffer and then grabbing one item and placing it throughout the array. The next method is just a simple insertion sort. Now the insertion sort works just like any other insertion sort would. This is going to be a sort method that's going to be used for arrays smaller than 16 items. Again, we are dealing with large arrays. Insertion sort will, worst case scenario, it usually runs at big O to the n squared time efficiency. But for smaller arrays that are arrays less than 32 items, insertion sort will actually run more efficiently than merge sort, which runs at O n log n time. So for these smaller arrays, when we break them into smaller blocks of 16, or even 4, or 8, or 32, insertion sort is actually going to sort that array, that subarray, faster than if it were merge sorted. Then we have a reverse. Now this reverse method is going to actually reverse a range within the main array. Again, remember, we are trying to sort this array in place. So what reverse typically does is just swap values in an array in reverse order. So it will return the array in reverse order. However, with an in-place merge, I don't need to reverse the entire array. I need to reverse only a portion of the array. And so what this is going to allow me to do is when I reverse that, it will actually allow me to create rotations within the main array. And when we talk about the rotation method in a few moments, we'll see how that reverse actually works. Then the next is a block swap method. Now this is going to take advantage of that swap method that I built earlier, but instead of just swapping one item with another, it's actually going to swap a range of items with another range of items that are of equal size. So if I need to move 3 items from the left end of the array to the right end of the array and vice versa, I can grab those items as a block and move them across the array. Then, as I said before, we are going to be using that reverse method that I built. That's a reverse within a range of the main array. This reverse, it's found that if you reverse a range of items 3 times consecutively, you can mock a rotation of the array, but only for that small range within the array. So you're not rotating the entire array, you're only rotating a portion of the array. Then one of the important major methods within this sorting algorithm is the merge. And again, a merge is just kind of like this zipper algorithm that compares values at each indices in the subarrays and then sorts them to where it wants to go. Now, when it sorts these items, remember what it's doing here is it's creating a buffer. Again, this is just that internal memory unit, and it's going to be built into the original array. And what it's going to do is it's going to cache those items that need to be moved in and out of the array into that new buffer. Now, again, this buffer is dynamically built, which could cause some leakage into using extra memory, but it should not be memory that goes beyond the ON memory unit. And once it's used, it's gotten rid of as soon as this merge is completed. Then we have several merge methods that are dealing with this whole idea as well. So again, when we have that buffer, or when we're trying to merge units within the array, we're going to need to merge two ranges from one array and save the results into a different array, and then we're going to set the array equal to the range that we're merging. So that, again, just another method to merge items within the bounds of the original array. As I said, there are a lot of methods here, and there are a lot of different merge methods, and so overall there's just a ton of merging going on within this this algorithm. Next is that merge external, and again we're creating an external buffer, and we're actually using the cache that we built when we first started this algorithm. So we have that memory that we can use, that 512 units of memory that we can use to kind of hold items in and then pull them out as we need. This allows us to keep place within that merge so that we understand where things came from and where they're going. And then once the cache is utilized, it's just set back to, or once it's utilized, then that merge has occurred and that memory can be reused for other subsequent merges. Then we talked about the merge with an internal buffer. What this merge with an internal buffer is going to do is it's going to allocate unique units within the original array. It's going to take those unique units and push them to the ends of the original array, and this will create buffers on each end, which we can kind of hold values and then swap values within the array as we need when we're doing a merge on or within ranges within the array. And notice that this merge internal takes advantage of that block swap. So we're actually moving entire blocks of units when we're doing these internal merges. Again, we've created buffers on both ends of the array, and we're going to be working with those buffers to take advantage of this. Then we have a merge method that will merge without a buffer, and this is going to actually be using the binary searches and that rotation. So we are going to locate items within the array, and then we're going to rotate sub-arrays within the array until we get that number in place where we need it, and then we can continue rotating numbers within those sub-arrays to sort numbers in the appropriate order. Then we have this net swap method, and this net swap method is to be utilized when we are actually grabbing larger blocks than what we want to deal with the block sort, and we are swapping numbers individually within a specified range. Now this actually uses a comparator that we've built in. Again, we're able to compare two seemingly disparate numbers within the array and then just swap them out as we need to when we work through this. Now the net swap will allow us to actually grab larger and larger units to swap with internally. And this is the buggy method that that we're kind of dealing with when we're working with those arrays larger than 32 units. So we're actually going to be using this in another portion of the merge. Okay, and then finally we get to our main method. Now this main method is just a bottom-up merge. So again, a bottom-up merge is typically an in-place merge using big O to the 1 memory. And what it does is it creates a merge within the array that allows swaps within that array using rotations and the merge method from above to actually deal with those arrays that are larger than 16 units. If an array is less than 16 units, then it takes advantage of that insertion sort that deals with smaller arrays very, very efficiently and very quickly. Okay, so again, as I usually do, I create a shuffled array of 10 random units between -100 and +100, and we're actually going to show you that this works right now. So let me go ahead and clear the screen, and we are going to run that Ruby method. So again, I'm still dealing with arrays larger than 16 units. There's a lot of moving parts in here once you get beyond the 16 unit threshold. However, when that occurs, we're dealing with numerous internal swaps that are going to just build upon one another, grabbing items and holding items within buffers and caches that have been preset to kind of contain within that O1 memory usage. Okay, so let's go ahead and run this block swap on those 10 random units. And as you can see, the random array that was thrown in was -48, -60, 65, 46, -44, -20, 35, -72, -89, and 95. And then returned is -89, -72, -60, -48, -44, -20, 35, 46, 65, and 95. Okay, so as you can see, that array has been sorted, and it's not a fluke. I didn't code in the array to be any sort of specific thing. I passed in another random array and another, and so we can see that this method does actually sort arrays, and it can actually sort arrays, I believe, up to 16 units at this point, but anything bigger than that, and it starts to have leakage and issues in the buffers themselves, which we're still dealing with, but right now this method works for those smaller type arrays. So again, just to show you what might occur once we get beyond that 16 unit threshold, so let's say we want to do 20, we can run it, and as you can see toward the end of the array, those last 4 units, that last smaller block, it has an issue putting that in place. Again, that's mostly a bug right now with how the buffers are sorting and working, but still building it out, still dealing with it. But again, as per the spec right now, this will actually work, and we can prove that by going ahead and showing you that that spec works. So let me clear the screen one more time and just run that RSpec. And then specifically, we're going to run the spec file, and this is block sort spec.rb. And as you can see, we get block sort moves the largest integer to the end of the array, all the way to handles negative numbers appropriately. So we get 7 examples, 0 failures, and the array is complete. Again, still a little bit of work to do on this block sort method. We've still got to get those merging issues taken care of with that buffer and cache. So still a lot of code to write and build out. But right now, this method will pass the spec that was sent to us specifically. So again, if there are any questions, please feel free to send them my way, and I will get that taken care of and answered as best I can. All right.